Hello everyone, welcome to the lecture series on IC applications. So far, if you observe, we have seen some introduction regarding integrated circuits, and then the most important component are the circuit present in the IC, integrated circuit. Even if you consider any basic IC, the circuit is nothing but differential amplifier. So we have seen different types of differential amplifiers. Basically it is available in 4 modes. So depending on the nature of the input and output, we have seen dual input, balanced output configuration, also seen single input, unbalanced, single input, balanced output, dual input, unbalanced output. Various types of differential amplifiers have been seen, and we move further towards the analysis of differential amplifier. So that is DC analysis as well as the AC analysis. We have seen DC analysis is nothing but differential amplifier is also an amplifier, saying we need to operate the circuit. We need to operate the circuit in a specific region of operation. That is nothing but what we can say cutoff region, saturation region, and active region. So it is also an amplifier. So we need to operate the circuit in the specific region, preferably active region. So under DC analysis, we are able to fix the Q point. So determining the expressions for VCEQ, determining the expressions for VCEQ as well as ICQ. So this will set the Q point of the amplifier, any amplifier. And here also we are able to find the expression for VCEQ as well as ICQ under DC analysis. Also the analysis is carried out for AC configuration. For AC, what is by AC analysis here? So here we are going to determine the expressions for gain. So we said there are 2 different types of gains. What are they? One is AD and the other is going to be the AC. So we have common mode gain as well as differential mode gain in the case of the differential amplifier. So these are the most important components of an IC, and now we are going to deep dive into the basic integrated circuit. So we can say this is the very first integrated circuit, that is nothing but the operational amplifier, which is going to be the operational amplifier, also called as op amp. So in the simple form, it is also called as operational amplifier, that is op amp. Very popular as op amp. Okay. So what is the block diagram of this basic IC? What is the block diagram of this particular operational amplifier? If you observe, it consists of 4 number of stages. So this can be the first stage, and this can be the second stage, and this is your third stage, and this is your final stage and the 4th stage. So if you observe, the first stage is going to be the input stage. So input stage, and unlike any other amplifier circuits, so this operational amplifier consists of 2 inputs. So in the first stage, so we are going to provide 2 number of inputs. What are the 2 inputs here? So one is the non-inverting input and the other is going to be the inverting input. Non-inverting. Now what is my non-inverting? Non-inverting means we are going to provide plus V. Whatever the signal that you are going to apply to this particular terminal is supposed to be the plus. That is nothing but positive voltage, positive signal we are going to provide here. Is nothing but non-inverting input. And the other input is going to be the inverting. Inverting means we are going to provide a negative voltage that we are going to provide this to this terminal. So do remember, this operational amplifier consists of 2 number of inputs. What are the 2 inputs? One is the non-inverting input, which is supposed to be plus V, and the other is going to be the inverting input, which is supposed to be the negative V, right? So these 2 are the inputs that we are going to provide to the input stage of the operational amplifier. And what is input stage? What is input stage? The first stage. It is supposed to be a differential amplifier. So do remember, the input stage of the operational amplifier is going to be the differential amplifier. Preferably, it is going to be the dual input balanced output configuration. Preferably, it is going to be the dual input balanced output configuration. What is meant by the dual input? So both the differential amplifier, both the transistors. We know that a differential amplifier consists of bipolar junction transistors, right? Both the transistors are going to have the input, that is called the dual input, and it is going to be the balanced output. What is meant by the balanced output? Both the transistors are going to provide output. So preferably it is going to be the difference output. So do remember, the differential amplifier which is used in the first stage, is going to be the dual input balanced output configuration. We will discuss further more details about the input stage, right? And coming to the intermediate stage, the second stage of this operational amplifier is going to be the differential amplifier, named as the intermediate stage. Second stage, usually termed as the intermediate stage, it is going to be the differential amplifier once again, and it can be dual input unbalanced output. So thus in the intermediate stage consists of a differential amplifier. It can be dual input and unbalanced output. What is meant by the unbalanced output? So no need to consider both the outputs. It is not required to have both transistors output. It is enough to consider only one transistor output, right? Usually this differential amplifier consists of two number of outputs. What are they? We will call it as VO1 and VO2. So if it is your balanced output, both are significant. Both output voltages are significant. If you consider unbalanced output differential amplifier, the output can be either VO1 or it can be VO2. That is the output from any one of the transistor can be and is considered for the analysis. So do remember, in the intermediate stage we are going to have differential amplifier which is under dual input unbalanced output configuration. Now coming to the third stage is going to be the level shifting stage or triggering level shifting stage usually. So what it consists of? This stage usually consists of emitter follower with current source, with constant current source. So this stage consists of emitter follower with constant current source, right? So more details about this we will discuss in the upcoming slides. So do remember, level shifting stage. What is the purpose of this particular stage? What this stage will do in operational amplifier, that we will see in the upcoming slides. So what type of circuit we are going to have here? It is going to be the emitter follower. So do you remember what is meant by the emitter follower? Emitter follower is nothing but, if you remember, it is going to be the common collector configuration. Usually emitter follower is nothing but the common collector configuration. So which is supposed to be considered as a constant current source. So these are the characteristics of the circuit which we consider under level shifting stage. Now coming to the fourth stage. So fourth stage is supposed to be the final stage. Of this operational amplifier. It is preferably, what kind of circuit we are going to have? What circuit we are going to consider here as the final stage? It is going to be, about the high level signals. That is, we have small signals as well as the large signal amplifiers. The output stage is supposed to be the large signal amplifier. The fourth stage of the operational amplifier is supposed to be the final stage. So what circuit we are going to consider here in the final stage, that is output stage, is going to be the large signal amplifier. You know about the large signal amplifiers. So in the basic amplifier itself, you can consider that as a small signal amplifier as well as the large signal amplifiers. What are large signal amplifiers? If you remember, large signal amplifiers are nothing but class A amplifiers, class B amplifiers, class C amplifiers, like that. And again in class C and class B there is a subdivision. So here we are going to consider complementary symmetry push-pull amplifier. It is supposed to be the large signal amplifier. The purpose of large signal amplifier is nothing but it is there is a tendency to increase the signal multiple times than that of small signal amplifiers. Small signal amplifiers, they have a tendency to amplify the signal over a limited value, whereas these large signal amplifiers will amplify the signal over a large or multiple times. They will amplify the signal to the multiple times. So that is the purpose we are going to use this complementary symmetry push-pull configuration as the output stage of this basic operational amplifier. So we will see each stage more detail here. Now coming to the input stage. So what we said about the input stage. So the input stage of op-amp is responsible for receiving and processing the input signal. So what are the responsibilities of this input stage? This will receive the signal. So what signals we have here? We have both plus V as well as minus. We have both non-inverting as well as inverting signals. So this stage will receive these signals and will process further as input signals, so which are supposed to be amplified in the next stages. Also the input stage typically consists of, so what we said, it consists of a differential amplifier which amplifies the difference between the two input signals. And we said it is going to be the dual input. What is by the dual input? Whatever the input signals we applied to the input stage are valid, and here the difference of these two signals will be considered to amplify, right? These are some characteristics or purpose of this your input stage. And further, if you observe, the differential amplifier circuit which we use here consists of two transistors. That's what we said, no? So it is going to be the dual input balanced output. So we are going to use the two transistors, and the two transistors have a significant role. No transistor is neglected simply. Both transistors are considered for the input operation as well as the output operation, right? And are supposed to be BJT or FET. So that is both the transistors can be bipolar junction type or field effect transistor type. So which are configured in a way that amplify the difference between the two input signals, right? And further, if you observe the input stage, you can notice that the transistors usually biased. So we know that how the transistors will function, how the transistors will operate. They need a bias. They need a bias along with the input signal. They need a bias. So bias in such a way that they operate in the linear region, preferably in the linear region, that is nothing but the active region, so that the output signal is a faithful representation of the difference of the input signal. So it is not the faithful representation of the input signal, rather it is going to be the faithful representation of the difference of the input signals. Since we operate the two transistors in the linear region and nothing but the active region of the output characteristics of the transistors, right? And further, if you observe, the input stage of op-amp may also include other components. So what are the other components? So tell me, is it enough to have only transistors to meet the requirements as the first stage? No. Along with the transistors, we need resistors, capacitors. It may be required to have diodes to overcome some additional drawbacks, because you are in the input stage. The input stage may have some excessive currents, that may damage the entire circuit configuration. So you can use the diodes as a current limiting components, because these diodes may absorb the excess amount of currents that are available in the first stage, or the excess currents drawn by the input stage, so that you can protect the differential amplifier circuit damaging from excess currents. And further, if you observe the input stage, it is all about the biasing. It consists of some amount of biasing networks so which are set for DC operating point. While the input protection, we may use the diodes. So that is the input protection circuit may be your diodes. So which will act as a current, excess current protection. If there is any excess amount of current drawn in the or applied or provided in the input stage, these diodes may absorb those excess amounts of currents, and you can protect the input stage. So what is there in the input stage? That is nothing but the differential amplifier, right? So do remember, the input stage consists of basic transistors. What are the basic transistors? So which are operated under differential amplifier mode, preferably dual input balanced output configuration. And another point to remember here is, along with the transistors, it also consists of basic circuit components such as resistors and capacitors. Also it consists of current protecting devices or components such as diodes. Now coming to the next stage, what is the next stage in the block diagram? It is going to be the intermediate stage. The intermediate stage of op amp, what is the responsibility? So we have seen the first stage. First stage is nothing but the input stage. What this stage will do? This will receive the signal, this will receive the input signal and process the signal further. And coming to the intermediate stage, what is the responsibility? It is responsible for further amplifying and shaping the signal that has been processed by the input stage. So what we are going to do in the intermediate stage, what this stage will do, what are its responsibilities? If you observe, so see, in the input stage itself, we are able to amplify the signal further. We are able to amplify. What signal we are going to amplify? The difference signal we are going to amplify. And in the intermediate stage, we are going to amplify the difference signal further, which is processed by the input stage, right? And the intermediate stage is typically one or more amplified circuits. Not necessary to be only one circuit, because it depends on the amplification factor. How much amount of signal you want to amplify, right? So you know about the cascade configuration of amplifiers. So what is the cascade configuration of the amplifier? You may have first stage, second stage, third stage, like that. You can have n number of stages. So all these are nothing but amplifier, first stage, second stage and third stage. Yeah, I can say A1, A2, A3 and A4, which are all connected in cascade. So what is this cascade configuration? So this is first circuit, second, third and fourth, like that we can say. So what this will do? So the first stage will amplify some amount of the signal. Second stage will amplify further. Third will amplify further, and fourth stage will amplify further. So it all depends on how much amount of the amplification factor you want to achieve. So it all depends on the requirements. So that's why the intermediate stage is basically responsible for further amplification of the input signal. So it depends on the requirement. It may be one circuit or multiple. It may be one or multiple circuits are possible in the intermediate stage as the intermediate stage. So do remember, it is all about the requirement, how much amount of gain you want to achieve, right? And in many op amps, intermediate stage is implemented using one or more amplifier stages based on the same and similar differential amplifier circuits as in the input stage. So don't think intermediate stage is some other amplifier circuit. No, not at all. This is very much similar to that of the input stage. This is very much similar to the input stage. So the signal is amplified to some level in the input stage, and this will be further amplified. The signal is further amplified in the intermediate stage. So this may have one or more amplification circuits, right? And these amplifier stages typically provide additional gain. Do remember, additional gain, bandwidth and output driven capability. So finally, whatever the amplification we achieve, in the intermediate stage, it is supposed to drive your load. That is, you are going to drive some external circuit which are connected at the output section, right? And allowing the op amp to produce a larger output signal than the input signal. So this is the primary consideration. The output which we obtain should be greater than the input signal. Understand? Only then we can say that there is a faithful amplification. So if you achieve output is less than the input, if you say output is less than the input, is it an amplification? No, not at all, right? So we need to meet the criteria. What is the criteria? Output should be far better than your input. This is what the requirement. Far better than input. I should say far better than, right? Not equal to or just equal or just higher than. No, it should be far better than your input signal. So in order to achieve this criteria, whatever the possible number of circuits are required, that we may consider under intermediate stage or within the intermediate stage, right? And in addition to the amplification stages, the intermediate stage may also include other components. So as usual, other than the transistors, you may consider resistors, capacitors, and there may be a feedback network. There may be a feedback network to sense the nature of your output signal. To sense the nature of the output signal, sometimes you may also require to have a feedback network. So because whether we are able to achieve the required output voltage or not. So these things you need to sense continuously. So you may have your a feedback network, which are used to shape the frequency response of the op amp to provide stability and control over the gain. Do remember, one of the most important characteristics of differential amplifier is stability. Stability and control. Stability as well as the control over the gain. So whatever the signal, whatever the output signal we achieve here is stable and have a good control over the gain. Understand? You know about the stability of the gain. See, the moment we say feedback, what will you understand? We are going to achieve some stability. We are going to achieve some stability in gain. That is nothing but in the operational amplifier. So as a summary, the intermediate stage consists of differential amplifiers. It can be more than one or many circuits. Purely depends on the requirement. That is how much amount of gain you want to achieve. And additionally, it may consist of feedback networks, because to ensure the stability and control over the gain, we may have your feedback network also. Now coming to the third stage in operational amplifier. What is the third stage? It is going to be the level shifting stage. Do remember? So with the first two stages, we are able to achieve the required gain. And now we are in the third stage, which is going to the level shifting stage. See what is this stage, what it will do, what are its responsibilities. So this stage is responsible for shifting the input voltage levels to a level that is compatible with the internal circuitry of the operational amplifier. So look at the name. What is the name of this stage? The name of this stage is level shifting. So what you are going to shift? The voltage levels. We are going to shift the voltage levels to the compatible range, to the compatible level within the internal circuitry of the operational amplifiers. So this stage is typically composed of voltage divider network as well as the buffer amplifier. So what it consists of? See, the purpose of this stage is very clear. So what is the purpose of this stage here? It is going to shift the voltage levels. It is going to shift the voltage levels. What is by shifting voltage levels here? See, if you draw a signal like this, so what will you say about this signal? This is symmetrical, of course. This is symmetrical with respect to the origin. So don't worry about the width of the signal in the negative cast and width of the signal at the positive peak. So ideally, I mean to say this is going to be some sinusoidal signal. I mean to say this is going to be some sinusoidal signal. What is this signal? Having certain peak values. Having certain peak values of the voltage. Right? And now this signal is symmetrical with respect to the origin. What is my level shifting here? What is meant by level shifting here? I want to shift this signal like this. I want to shift this signal above the origin, or I want to shift the signal below the origin. I want to shift the signal below the origin. Both are possible, right? Both are possible. You may shift the signal either above the origin, or you may shift the signal below the origin, a sinusoidal signal. This is nothing but level shifting. You can shift, this is just a kind of brief about the level shifting. So what you need to understand here is, if you want to shift the voltage levels, so you may ask the question, why we need to shift? Why we need to shift? It may be required to reach some compactable range. So not necessary to have the signal symmetrical with respect to the origin. Sometimes that is what the shaping of the signal. So what it is, a shaping of the signal. Sometimes you need the signal above the origin completely, or sometimes you need the signal below the origin completely. Right? This is what the shaping of the signal. And this is consists of a voltage divider network as well as a buffer amplifier. You know about the buffer. It will do nothing other than processing the signal from one end to other end. So what it will do, it will process the signal from one end to other end. That is nothing but the buffer stage. And the voltage divider circuit consists of course, resistors, with one resistor connected between the input signal and ground. The other resistor is connected between the output of the buffer amplifier as well as the ground. This is just the circuit configuration of the voltage divider network. So what we said, it consists of two resistors. See, the moment you say voltage divider, what is meant by the voltage divider? How will you achieve the concept of voltage division? Using a capacitor will you achieve the voltage division? No. Using inductor? No. So we need a resistor. So if you want to perform voltage division, we need a resistor. So here this particular voltage divider circuit consists of resistors. So do remember, voltage divider circuit generally consists of resistors. And here this circuit consists of two resistors. So we have given the configuration of the two resistors. What are they? One is connected between the input signal and ground. The other resistor is connected to the buffer as well as the ground. So this is about the intermediate stage. Level shifting stage. Further, the output voltage of the voltage divider is then fed to the buffer amplifier. So primarily, this level shifting stage. So what is the purpose here? It is nothing but shaping. Level shifting is nothing but shaping of your amplified signal coming from the intermediate stage. It consists of voltage divider circuit as well as the buffer amplified stage. So the output of the voltage divider is connected to the buffer amplifier. So the buffer amplifier here is, so we are going to give the characteristics of the buffer amplifier. What it is high gain amplifier with high input impedance as well as the low output impedance. So these are some characteristics of buffer amplifier. It is going to have the high gain, high input impedance and low output impedance, right? And it is designed to isolate. We are giving one more characteristics of the amplifier. It is designed to isolate input signal from rest of the op-amp circuitry while amplifying the signal to a level that is suitable for further processing, right? So isolate this signal from other components, other op-amp circuit components, and amplify the signal and process the signal further, right? This is nothing but your level shifting stage, and some other parameters, other characteristics are nothing but. So when the input signal is applied to the voltage divider circuit, it is divided into two parts. So one appearing at the output of the voltage divider, and the other part is being dropped across the resistor connected to the ground. Just we are going to characterize the nature of your voltage divider circuit and its operation. the output of the voltage divider is then amplified by the buffer amplifier, which shifts the signal level to a level that is compatible with the rest of the op-amp circuitry. So do remember, this is nothing but shaping of the signal with amplification. So that's what we are going to do under level shifting stage. And further, if you see, the level shifting stage is important. Why we need to consider the level shifting stage? Why we need to consider level shifting stage in the operational amplifier block diagram? Because it allows the op-amp to process the input signals that may have different voltage levels. Very, very important. That may have different voltage levels than op-amp's power supply voltage. See, so the circuit may have different voltage levels. If it is so, then it is very difficult to handle such different signals, right? So without level shifting, the op-amp would not be able to process the signals that are outside of its input voltage range. So it is must. So this is the conclusion we can draw out of it. Level shifting stage is must, because so you are going to have different voltage levels, different voltage signals. It is very difficult to handle such typical signal nature, right? So it is required to level nothing but shape. We need to shape all these voltage signals, right? And coming to the last stage, or the final stage, coming to the final stage of the operational amplifier is nothing but the output stage. So it is responsible for amplifying the voltage difference between the input signals and driving the output load. So do remember, this is the final stage of the operational amplifier, which is connected to the load. So from here you can connect the signal to the load. It can be whatever the device you want to connect at the output terminals of the operational amplifier that can extract this particular amplified signal, right? The output stage typically consists of large signal stage. The output stage is preferably a large signal stage, and it consists of push-pull amplifier configuration, or class AB. Class AB is nothing but the large signal amplifier stage. Okay, so it is not the small signal, it is a strictly large signal stage. And in push-pull configuration, again under push-pull configuration there are so many, right? So preferably we are going to have complementary transistors. These things you might have studied under power amplifiers, that is large signal amplifiers. So here we are going to use complementary transistors to meet the circuit configuration of push-pull configuration, right? So this is about the block diagram of operational amplifier. So do remember, it consists of input stage, intermediate stage, and then level shifting stage, and finally it is going to be the output stage. So whatever you are looking here, this is the diagram that represents your operational amplifier with more details. Okay, and this is the symbol. So what is the symbol for operational amplifier? As we said, there are two inputs. These are the inputs. So this is nothing but the non-inverting input. This is the non-inverting input, and this is going to be the inverting input, and these are the two bias voltages. So we said no. So we have two biasing levels. One is at VEE, and this is at VEE. You can consider, and this is the biasing at VCC, collector terminals. So what is VS minus here is you can think that this is VEE, negative biasing voltage, and this is nothing but the positive biasing voltage, right? Across the collector terminals we are going to apply. So VS plus and VS minus are nothing but two biasing voltages, and finally this is your output. Do remember, if you are working with operational amplifiers, it is required to provide both bias. There is no option. Do remember, there is no option. You have to provide both the bias. What are the bias here? One is the negative bias and other is the positive bias. We need to provide both negative as well as the positive bias. So what will happen if we ignore any of the biasing voltage? The amplifier will burn, the amplifier will never work, it will stop working, right? So this is a symbol for operational amplifier having two inputs. One is a non-inverting input and other is inverting input, and two biasing. See, this is optional. So how many number of inputs that you want to provide is optional, right? So in the next upcoming lectures we will see the operational amplifier itself classified into two. One is the inverting amplifier, another is non-inverting amplifier. So it is not very strict. So providing both the inputs is not strict. You may provide any one or you can provide both, right? Whereas biasing is strict. So you have to provide both positive bias as well as the negative bias. Okay, this is regarding the symbol of the operational amplifier, and we will look at the specifications. We will look at the specifications of operational amplifier. These specifications are classified into two. What are they? One is the ideal specification and other is the practical. So there are two types. One is the ideal and practical. So also we will call it as ideal characteristics and practical characteristics of operational amplifier. So briefly look at it. So the input resistance would be infinite. Do remember, input resistance of ideal operational amplifier is infinite and output resistance should be 0. So do remember, input. See, in any amplifier circuit, it is recommended to have high input impedance, and here the high is called as infinite. It should be infinite and the output resistance should be 0, right? And coming to the voltage gain, it is going to be the infinite. We are going to have infinite voltage gain, and the bandwidth would be infinite. Again, bandwidth would be infinite, and voltage of the two inputs are equal, then the output voltage is 0. So if the voltage on the two inputs are equal, that is V plus and V minus, both are input, output should be 0. Output should be 0, right? V out should be equal to 0 when both V in 1 is equal to V in 2. Both inputs are same, the output should be 0, very strict. So there should not be any fractional voltage will not be considered. It should never consider even the fractional voltage, that is 0.1 volts, 0.5 volts, 1 volt, 2 volts. No, it will never entertain. It is very strict to have 0. These are the ideal characteristics or ideal specifications of the amplifier. So what are they? Input resistance infinite, output resistance 0, voltage gain should be infinite, bandwidth should be infinite, and output voltage equal to 0 when both the inputs are same or when both the inputs are ideal. So coming to the practical characteristics, so the open loop gain of practical amplifier is around 7,000. Okay, the gain should be around 7,000, and practical op amp has non-zero offset voltage. It should consist of a non-zero offset voltage, that is the zero output is obtained. The zero output is obtained for the non-zero differential input voltage, and the bandwidth of practical amplifier is very small value. So unlike ideal characteristics, so here bandwidth is very small value. This can be increased to the desired level by applying adequate feedback signal, preferably negative feedback. You know that negative feedback will increase the bandwidth, right? If you want to achieve more bandwidth, increase your negative feedback, so you can achieve the required bandwidth. So these are the practical op amp characteristics. So in the next lecture we will see further, that is the DC characteristics and AC characteristics of operational amplifier. So these things we will see in the upcoming lectures. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.